In this video, I'm going to discuss the Metropolis algorithm. The Metropolis algorithm belongs to sampling methods, which try to simulate the distribution P through random samples. And these random samples are realizations of the distribution. So the key idea is to have this closed form representation of a distribution and turn it into a numerical simulation where we have representative realizations of the distributions. Having such samples makes it very easy to evaluate expectation values. So for example, if we want to evaluate the expectation value with respect to f, we could just take the average value of f evaluated on all our samples, as long as the samples are distributed according to our distribution P. And this is not only easy, it is also asymptotically independent of dimensionality, which is a key strength in high-dimensional spaces. However, it is not without difficulty. There's the issue that these x's actually have to be drawn from P for this to be valid. And the big question is, of course, how can we generate samples which are distributed according to our distribution P? The Metropolis algorithm is a very simple algorithm, and it just has two requirements. So let's start directly with first one, the proposal distribution Q. It is a distribution chosen by the user, and he must be able to generate samples, and the distribution must be symmetric. More on that later. On the other hand, we need a target distribution P with pointwise evaluation. So the algorithm's goal will be to use our simple and accessible known distribution Q and generate samples from it and filter them or turn them into samples from our target distribution P. And the result is then a stream of samples which is approximately sampled from our target distribution P. So the idea of this algorithm is to generate samples from a known distribution and transform them into samples of our distribution P, which we can only evaluate in a pointwise manner. The algorithm itself is very simple, so we can quickly walk through it. It starts by initialization. We just choose a value x to start from. Then the next step of the algorithm is to generate a new sample, always based on our current sample x. So we would draw first a sample x prime from our distribution Q, from our proposal distribution. And this x prime would be called a proposal. Remember, Q has to be simple enough to generate samples from it. Now, with probability given essentially by the ratio of our target distribution evaluated at that new proposal compared to the value of our current sample, we now accept the x prime as a new state, and we do this stochastically. So this gives a probability value, then we throw dice to actually decide whether we should accept it or not. We talk of accepted or rejected proposals. In the accepted case, we would take the proposal as our new current state x. The third step is then the actual sample generation. So given our current state x, we would emit this state as the sample. And this algorithm can be iteratively applied, so we just generate the next sample by going through these steps again. So steps 1 to 3. Let's look at an example, and here I picked an example you should all be familiar with. It is the 2D Gaussian distribution. So assume we want to generate samples from this 2D distribution, but we don't know how to sample P directly. So we would apply the Metropolis algorithm. In order to do that, we not only need our target distribution, but also a proposal distribution, which we would take very simply in this case just to be an isotropic two-dimensional Gaussian distribution. This kind of distribution would be called a random walk, since it is centered at our current state and just perturbs this current state randomly into any direction. Let's choose a few parameter values for our target distribution. Would be a mean and a covariance matrix, and here I've chosen a covariance which has an actual correlation between x and y. Now let's run the algorithm and generate samples. It will then look like this. What you can see here are all the proposals and samples generated by the algorithm. In red circles you see all the rejected proposals, and the accepted ones are actually connected by a blue line. And if you wait for the algorithm to develop, you can see that the samples at the end actually have this elliptic familiar shape of the 2D Gaussian we expect here. Now if we look at again on the proposal distribution, this distribution has a parameter. So there's a variance or a standard deviation involved here, which I just called sigma. And the example I've shown you was with the sigma equals 1. I could have chosen sigma differently, for example smaller as 0.2, and here the result looks a little bit different. You see that the algorithm now takes much smaller steps. The sigma is some kind of a proposal step size, but at the end it still reaches our familiar elliptic Gaussian shape. But we might have to wait a little bit longer for this to happen. Let's discuss a few properties of the Metropolis algorithm. The first one, it is an approximation method. So the samples we actually generate with this algorithm, they approximate P in an unbiased way, but they are correlated. So we do not generate IID, so identically independent distributed samples. One very cool feature about this algorithm is normalization. So remember, P is usually a probability distribution, so it has to be normalized. However, when using this Metropolis algorithm, we only need ratios of P evaluations at the proposal and the current state, and in this ratio the normalization actually cancels, so the normalization is not required for the algorithm. This is a key strength of it. The proposals are allowed to be dependent, which means the distribution of our next proposal sample can be depending on our current state x. And this is what makes the algorithm very powerful. This introduces a kind of a one-step memory into it. Given our current sample, we generate the next one. The proposal has to be symmetric for the Metropolis algorithm, which means that this dependency on the current state can be reversed. So going forward and going backward should have the same probability. But if we take this typical choice of the Gaussian random walk, for example, as before, then symmetry is fulfilled and this is not an issue. If we have an asymmetric proposal distribution, the algorithm can be easily extended to deal with that. So in the case where this proposal is not directly reversible, we would correct this in the acceptance probability used during the algorithm. The correction is rather simple, so this alpha value, which is the probability of accepting a new sample, would then just be extended to an additional part where an explicit correction of this transition ratios are made. And that's the only choice required. So the whole algorithm would then look like this, the same as before, but with this additional correction factor. The algorithm is very simple and the problem difficult. So it can be expected that we have a few limitations, and one of the most important limitations is actually that highly correlated target distributions can be a bit problematic. So the situation is depicted here. We have a target with a strong correlation in red, and our proposal distribution actually does not match this target distribution, which is the typical case. We want to use simple and accessible proposals. And actually the proposal should match the target as good as possible, since the algorithm is most efficient if the proposal actually is the target, but that's not the situation we want to apply it to. So we have to kind of adapt our proposals to the target a little bit at least. So for example, in the above example discussed, we would adapt the step size such that we can get the best out of the situation. The consequences of these limitations is correlation. So among the samples generated, we have a so-called serial correlation, which means that the generated sample depends on the last generated samples. And this is on one hand due to too many rejections. So if we have a proposal distribution here which is too large, so if it would be as large as this, then it often jumps outside the high probability target region and generates a lot of rejections. And in each rejection case, we generate the last sample again, leading to a duplication of a sample. The other issue where correlation can occur is if we have a step size which is too small, such as in the small step size example above, where we do not explore on a large scale. So we would only wander around very locally in this distribution, and thus all the samples are very similar as the last ones, because we do not propose to jump far enough. The Metropolis algorithm belongs to the Markov chain Monte Carlo methods. These methods all share that they design a Markov chain in the background such that samples from this chain follow the target distribution specified. And the concept of all of these algorithms is that they use an already existing sample to produce the next one. This is formally captured by this Markov chain structure. They are very powerful in general sampling methods, with successful practical applications in almost all fields where statistics and probability theory is important. And they have a rich history. They've been developed already in the 1950s. It is a whole class of algorithms, so not only our Metropolis algorithm, but also Gibbs sampling, slice sampling, and a lot more. The Metropolis algorithm is an algorithm which generates probabilistic samples of a target distribution. However, it has an additional structure beyond this purely probabilistic view. It actually formalizes a propose and verify approach. So if we look at the algorithm again, it splits into two parts. We first have a proposal part where we actually draw a possible sample from a unspecified proposal distribution. So this can be almost any distribution. In the second step, we verify these proposals using these acceptance ratios here and throw dice whether we should accept them or not. This is a verification stage, whether the proposals are consistent with our target distribution. And in practice, this turns out to be very useful to integrate proposals which are unreliable. So we can, for example, deal with heuristics which do not always give a good result but sometimes fail. And we can deal with unreliable data, since we always have this verification step afterwards. All these ideas give it an algorithmic advantage way beyond the purely probabilistic Bayesian concept.